everyone, welcome to Spring Quarter Algebra. This is either Math 483 or Math 560, depending on whether you're taking it as a graduate student or undergraduate student. If we were in person, I would make some banter to get things going, some small talk, maybe some some words of wisdom or something like that. But we're virtual, so I don't have anything interesting to say other than let's get started with the actual math. So, you may have heard this. The math that we do is governed by axioms, right? And they're called the Zermelo-Fraenkel axioms. So ZF stands for Zermelo-Fraenkel. And these are the axioms that govern set theory. For example, one of the axioms essentially says there exists an infinite set, right? I mean, so the axioms of set theory get the ball rolling when it comes to sets. They tell us how to make unions, how to form sets, and so on. And so we have the axioms of set theory are essentially what our mathematics is based on. So that's the ZF. There's also one additional axiom called the axiom of choice. And so I want to talk a little bit about the axiom of choice. You may have heard, I'm sure you probably heard the words, but there's very few classes where you'd actually study or learn about the axiom of choice. In this class, you're going to learn about it. So a little bit of preliminaries here. So our first definition, the Cartesian product of the family of sets, let's say, so I'm going to take a collection of sets X sub alpha indexed by some indexing set script A. That's a script A right there. I know this drives students nuts, but I like to do it. So that's my script A right there. So practice that one for a second. Or if you want, use this one, I think you can do that script A if you prefer. But this one looks cooler, so you should use that one. Okay, so I'm working on a definition here. So the Cartesian product of the family of sets, X sub alpha. All right, I need to finish this sentence, but let's think, how do we normally think of a Cartesian product of sets? Well, if we have the set A and B, we talk about the Cartesian product A cross B, and we say it's the set of all ordered pairs of the form A comma B. Fine. If we have A, B, and C, right, then it's the set of things A, B, C. Great. So if you just have 2 sets or 3 sets or 5 sets or 10 sets, you can think of the Cartesian product as a collection of n tuples. But what happens when you have an infinite collection of sets and you want to create the Cartesian product? In particular, what happens if the number of sets, and I can't even say number of sets now because we're talking about an infinite collection, what if the family of sets is actually uncountable, meaning that our indexing set is uncountable? Well, now, okay, what exactly is a tuple? When we need an infinite number of entries, in fact, we need an uncountable number of entries. It just doesn't make sense anymore. So we need a more advanced definition for what the Cartesian product is. So the Cartesian product of the family of sets is the set, all right, so the Cartesian product of a set is a set itself. It's denoted with a capital pi, subscripted by alpha element script A, X alpha. And it is, by definition, a set of functions. And it's the set of functions, or the set of all functions, from script A into the union of the X alphas under the condition that F of alpha has to be an element of X of alpha for all alpha in script A. So that's kind of not a mouthful, but it's not obvious that in the case that we're taking the Cartesian product of a finite number of sets, that it actually boils down to a collection of tuples. So let this sink in for a second. So what do we have? The Cartesian product is a set of functions from the indexing set to the union, where we require the output when we plug in an element here to live in the corresponding x of alpha. So what I want to do now is show how this really does fit with our usual definition of what the Cartesian product is in the case that we have just a finite number. So let's say it like this. Okay, let me put it up here. So we usually identify a particular function. So let's say identify elements of the Cartesian product, let's say the product, with their image, with their collection of outputs, right? And we typically write it as tuples. So let's say written as T-U-P-L, tuples. Some people pronounce it tuples. I guess I say tuples. I was just arguing with some people a few days ago about that, and I wasn't sure which one I used, but it turns out that I used tuples. So for example, so let's just say, all right, let's look at the easy. So let's say that x sub 1 is equal to the collection A, B, C. So there's my first set. And x sub 2 is the set consisting of the integers x and y. Okay, now if we took, right, if we were back in any class before this one, we'd say, okay, x1 cross x2 is a collection of ordered pairs, right? So for example, the ordered pair A comma x lives inside this thing right here. Now how do we square that? Square this notation here with this right here, where each element of the Cartesian product is actually a function. And notice we typically, for a finite collection, we just write a little x in between here, a cross right here, right? This is the more advanced notation when we're talking about more general Cartesian products. So what is this? Well, this element right here, A comma x, we can think of, and this is what we were saying up here, that we usually identify the elements with their images written as tuples. So A comma x, this one corresponds with the function f. Now let's see, the domain of the function is the set of subscripts. So in this case, we have the subscripts 1 and 2. So it corresponds to the function that goes from 1, 2 to the union. Well, the union is going to be A, B, C, X, and Y, where, all right, so such that f of 1 equals A and f of 2 equals X. All right, so what do we do then? We arrange the outputs as an ordered pair right there. Right? So we think of the function right here that gives an output of A for 1 and an output of X for 2. We write it, we think of it as the ordered pair, but what we're really doing is just writing down in order. Right? Put the A first because it corresponds to 1. Put the x second because it corresponds to 2. We think of the function, or we write the function, right, by just displaying who the outputs are. Okay, so that's typically the way we would, there's our definition. And now let me give you a couple of more advanced examples. So there's the product, the Cartesian product, and now let's say that our indexing set is the set of natural numbers, and for each natural number, so I want the Cartesian product of the an infinite collection of integers, sets of, how should I say this, copies of integers, right? So you could write this also, and we often would write this as z cross z cross z cross dot dot dot, right? An infinite Cartesian product of sets of integers. Okay, so who is this? Well, okay, technically it's a set of functions from the natural numbers to the unions of the integers, so that the output under each natural number is an integer. So we usually identify this, right? So we identify the function f from n to the union of a bunch of copies of the integers, which, by the way, right, the union of a bunch of copies of integers is just the integers. We identify a function with, let's say, an n1, comma n2, comma n3, dot, 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 an infinite tuple. First entry corresponds to the first output. Second entry corresponds to the second output, and so on. But it gets a little bit, at some point, using tuple notation gets a little bit clunky. So, for example, if we have product, let's say now, let's say in Z. Do I want to do integers or? Oh, yeah, that's fine. So now, what does a typical element look like, right? So a typical element is going to be an infinite tuple where we have dot, 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 and then we would have an n sub minus 2, and an n sub minus 1, and an n sub 0, and an n sub 1, and an n sub 2, dot, 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 dot. Whoop. It gets a little bit messy here, and so typically now, what we would really do is identify this. We often will just write it like that, as a single parentheses around an n sub alpha, and just think of this, okay, if you want, you can think of this as an infinite tuple where we stretch in both directions. Now you could make this, okay, so fine, we can do this, but now, because z is countable, this z is countable, we can write this out. But now, what if I do the Cartesian product, where now we would like to have a real number's worth, right, or a real line's worth of copies of integers. Now, there's no way to write this as tuples. We can identify the element, so I can write an x sub alpha here, right, where each alpha, where each, or let's say where x sub alpha is an element of z for each alpha in R. Okay, so anyways, that's the idea behind a Cartesian product. Well, that's the definition of Cartesian product. And with this definition, I can now state what's known as the axiom of choice. And it goes like this: if x sub alpha alpha element alpha is a family of non-empty sets, so we're requiring each of the x sub alphas to be non-empty. Then the Cartesian product of x sub alpha is non-empty. The axiom of choices actually can be stated in various ways. This is really sort of the down and dirty, quick way of stating the axiom of choice, right? It says that anytime you take a family of non-empty sets, the Cartesian product is non-empty. Now, what does that mean then? Okay, so the Cartesian product, that's a collection of functions. And so what it's saying is, no matter what family of sets you have, there's at least one function in here. So let's just kind of expand on that. So that is, there exists a function f from alpha to the union of the x of alphas, where f of alpha is an element of x of alpha, and such an f, there exists at least one function, and such an f is called a choice function. So let's say f is called a choice function. And now, so what's going on with this choice function? What it is saying, here's another way to think of the axiom of choice. That what you can do anytime you have a family of non-empty sets, you can take one element from each of those and lump them together into a set. Let's say that again. Right? The axiom of choice asserts that no matter what family of sets you have, as long as each one of those sets is non-empty, you can reach in and choose one element from each of those. So there's an x of alpha. Take an element, put it in your pile. There's an x of beta. Take an element out of x of beta, put it in the pile. There's an x of gamma. Take an element, put it in the pile. The axiom of choice says, no matter which family of sets, non-empty sets you have, you can take, there exists a set that has exactly one element from each of the x of alphas. It seems very intuitive, especially when I describe this. Take something, put it in the pile. Take something, put it in the pile. The problem is, when this set becomes uncountable, that act of take one, take one, take one, there's no nice ordering or no nice way to do that. And so, you can't actually prove that this is true. We have to assume, we assert that this is true. As an axiom, what we're doing is we are saying in the mathematics that we do, this is a true statement. It's an axiom. It's not something that we prove. Now, okay, so that's the axiom of choice. It turns out that in mathematics, there are a whole bunch of equivalent statements, equivalent to the axiom of choice. There are many, let's say results. I mean, yeah, okay, we'll call it results. In mathematics that are equivalent to the axiom of choice. And I'm just going to list a few of them. One of them is well ordering. And so, meaning, or what that means is that every set can be well ordered. You got to remember back to Math 248. What does it mean to be well ordered? It means that every non-empty subset has a least element. Right? So, typical sets that are not well ordered under their usual ordering, like the integers, right? The integers is not well ordered because there exist subsets, non-empty subsets of the integers that do not have least elements, right? So this well ordering asserts that there exists an ordering of any set you like. It doesn't matter what set you have, right? for which under that ordering, right, the set is well ordered. Another one, it's called Zorn's lemma. We're going to talk about that a little later. So Zorn's lemma, you probably heard, at least heard the word Zorn's lemma. We're actually going to study this a bit. Another one, what else is there? Every vector space has a basis. So there's one for linear algebra. There's one for topology. It's called Tikhonov's theorem. So if you've had topology, Tikhonov's theorem, which says that the product of any collection of compact sets is compact. So if you've had topology, that would make sense. If you haven't had it yet, that wouldn't make sense. What else? Oh, here's one from graph theory. Every graph has a maximal tree. And this list goes on and on. So here's the idea. We typically work with the Zermelo-Fraenkel axioms plus the axiom of choice. And with that as our usual basis for mathematics, you can prove any one of these statements, right? You can prove well ordered. You can prove Zorn's lemma. You can prove every vector space has a basis and so on. But you could also say, you know what, I don't really like the way the axiom of choice is. I would like to do the Zermelo-Fraenkel axioms, but I would like to replace it with one of those on the list. Go ahead. If you want to replace it with Zorn, fine. Then you will be able to say, okay, well, we put Zorn's lemma, we're treating that as an axiom, and then we can prove the axiom of choice. Or you could say, nah, I like Zorn's lemma right where it is, but I don't like the axiom of choice. I would prefer every vector space has a basis. And so, with this one, I can replace, let's say vector space, let's just say basis. And so what I could do is I could say, you know what, in my mathematics, I'm going to work with the following thing. Zermelo-Fraenkel axioms plus the axiom that every vector space has a basis. If you do that, then you can say, okay, we could prove from that, we could prove Zorn's lemma. It'd be kind of a pain, but yes, we could prove Zorn's lemma. We could also prove, what do I need? Oh, I could put the axiom of choice there, and then I could prove the axiom of choice from the assertion, the axiom that every vector space has a basis. Right? So that's what I mean by there's many equivalent results. Okay, so we need some definitions now. So a relation capital R on some set capital A is antisymmetric if for all X and Y in capital A, we have X equal to Y whenever X is related to Y and Y is related to X. Right? So any relation that has this property, that whenever you happen to know that X is related to Y and Y is related to X, it forces you to include that X equals Y, then we say that that relation is antisymmetric. There's lots of familiar examples of antisymmetric relationships. In fact, so the relation, the standard less than or equal to relation on the real numbers is antisymmetric. Right? If you know that X is less than or equal to Y and Y is less than or equal to X, then you conclude that X is equal to Y. Another one So the subset relation on the power set of any set X, right? So if you take the collection of subsets of X, right, then subset is also antisymmetric. And so what are we saying there? Symmetric. We're saying anytime if you know that A is a subset of B and B is a subset of A, then you conclude that A is equal to B. All right, so that's antisymmetry. You may have seen this definition before if you've taken some discrete math class, or I think I covered it in Math 248 last time. Yeah, we covered it in Math 248 last time also, I believe. So now, our next definition, a relation, and I'm going to use the symbol that looks kind of like less than or equal to, but I'm going to put a little bend to it, so a little curvy thing. A relation, but I'll refer to this often, I'll just refer to it as less than or equal to. You want to think of it as sort of a generalization of less than or equal to. So a relation, use this symbol right here, on a set capital P is a partial ordering of P if our relation is reflexive, antisymmetric, and transitive. All right, so notice we focus more on equivalence relations, right? Equivalence relations are those that are reflexive, symmetric, and transitive. If you replace symmetric with antisymmetric, then you call it a partial ordering. And then a little piece of terminology. So if you have a set together with a partial ordering, we call that set a partially ordered set or poset. So a set P together with a partial ordering is called a partially ordered set, or, and this is very common even though it's kind of a funny thing, or poset. Now, most of the time what we'll do is we'll just say let P be a poset, and it's understood that there's a partial ordering running around. Sometimes, so we'll just say occasionally we'll use this notation, ordered pair notation, P together with its partial ordering, right? So sometimes we'll just say, we'll write it like this if we need to be explicit that we've got a partial ordering. But most of the time we'll just say, let P be a partially ordered set, and then it's understood that there's a partial ordering. We'll have to specify what symbol we're using, which particular partial ordering we're using. So for example, so less than or equal to is a partial ordering of any power set. So for example, a subset is a partial ordering. Oh, let me phrase this a little bit better. How about this? The power set of the real numbers is a poset under the partial ordering that you get from the subset relation. And so we could write this if we wanted like that using ordered pair notation. This would be saying we've got a partially ordered set consisting of the power set of the real numbers together with the relation subset. So next, So let's let P be a poset under a partial, I'm just going to use the generic symbol right there, so under the partial ordering. Think of this as a generalization of less than or equal to. So then our partial ordering is a total order if for all, say, x and y in P, x is related to y or y is related to x. Or I could say x is less than or equal to y or y is less than or equal to x. And it's probably best to provide a non-example. I mean, if you think of numbers, right, like real numbers, the typical less than or equal to is a total ordering of the real number. So in fact, let's say that. So less than or equal to is a total ordering of the real numbers. Subset is not a total ordering of the power set, let's say the power set of the real numbers. And the reason, right? So what is this saying, this definition right here? When you have a total ordering, what it means is that you can always compare elements, right? One is always bigger than the other. One is always related to the other in one way or the other. And so subset is not a total ordering, and here's the reason. If you look at, say, the open interval from 0 to 1, that's a subset of the real numbers, and it's not a subset of 1, 2, and 1, 2 is not a subset of 0, 1. Right? And so what we have is they are the two elements, the ordered pair, or not the ordered pair, the subset 0, 1, the open interval 0, 1, the open interval 1, 2, those are elements here for which they are not related in either direction. Right? There are incomparable elements. A little bit more terminology here. So let's let P be a poset under our partial ordering here. So 3 parts of this definition: a non-empty, totally ordered subset of P. It has a name that's called a chain. So this is a chain. Part B of this definition, let me put it over here. So an upper bound of a subset, let's say S of P, is an element little u in capital P, such that let's say X, and I just want to say less than or equal to because you want to think of it as a generalization. So X is related to U whenever, or for all, little x in capital S. So think of it, an upper bound is somebody that's bigger than everybody inside S. Right? And then part C, an element little m in capital P is maximal if for all x, if for all x in P, x is equal to m whenever m is less than or equal to x. Right? So the idea is that you have no element that is strictly larger than m. Right? Anytime you see this symbol right here, it forces you to include that they're actually equal. Okay, so let me give you some examples now. So let's consider, so let's say, let's look at the power set of the real numbers. So that's all subsets of the real numbers, partially ordered by inclusion. And I want to consider, so let's consider this set right here. Let's call it C, and it's going to be equal to the set of all sets of the form. So these are going to be open intervals 0, comma 1 minus 1 over n, where little n runs through all the natural numbers. Right, so it's a collection of open intervals. This is definitely a subset of, well, no, it's not. It's really, no, it's not. Oh, yes, it is. Of course it is. It's a subset. It's not a subset of the real numbers. It's a subset of the power set, though. So now, let's think about what this looks like, right? What does C look like? Well, okay, so when n equals 1, we'll have 0, comma 0, the open interval from 0 to 0, that's the empty set. And then, okay, when n equals 2, we'll have 0, comma 1/2. When n equals 3, we'll have 0, comma 2/3. When n equals 4, we'll have 1 minus 1/4, which is 3/4. So, and notice that this goes on forever. It's this nested collection. That's what a chain is. All right? It's a collection of elements that you can line up like this, essentially, right? And everybody is comparable to everybody else, right? If I take any two elements in this set, I can say, one is larger than the other. One is contained in the other. Right? So there's an example of a chain. And then a couple of observations. So let's say observe. So the first observation, 0, 1 is an upper bound for C. 0, 1 itself does not live in this set, right? But it is a subset, right? So it lives in the power set of R. And it contains every single set in this list. Every one of these elements lives inside here. And that, if you look at the definition of upper bound, right, that's what it means. But it's not the only upper bound, right? So is, we'll say so is the interval from -1 to +1. All right, so is R, right? There's a whole bunch of upper bounds. So upper bounds are not unique in any sense of the word. A second observation, R is the only maximal element of power set of R. Yeah, let's look at another example. Let me just check the time here. Oh, I've been going for a while, huh? Okay. I'm just going to do a couple more examples and then we'll finish up. So next example. So let's let Q be the set of proper subsets. The set of proper subsets of R. So remember, power set of R, that's the set of all subsets of R. So Q encompasses all the elements of the power set except for R itself. So we can say, Q is equal to the power set of R minus R. Oh, I guess I mean. No? Wait, yeah, set containing. All right, so what I want to do, I want to delete R from this list right here, right? So I only want proper subsets. Now, so what? So if X is an element of R, then here's what I want you to notice. Then R minus X is a maximal element of Q. All right, so just sort of think about that one right there. I guess I want to just sort of put that in parentheses. And then let's finish with one more example. Oh, and I guess I should get to the point also. So let me do an example, and then I'm going to state one fact. So if you like. So another example. So let's let P be the set of subsets of the integers. So this is a set of all X subset of Z, such that X has finite cardinality, right? So it's the set of all finite subsets of the integers. And I want to partially order this. So let's say partially ordered. So partially ordered by the usual thing, inclusion. And let's let S be the set of all elements of P, of capital P, right? Meaning it's going to be a finite subset of the integers such that the cardinality is even. All right, so take all finite subsets of the integers that consist of an even number of elements. Then S has no upper bound. Right? There is no subset of the integers, finite subset of the integers, that contains every one of these. And P has no maximum element. So you should, sort of write up little mini proofs of each of these two facts right here. And then let's end with the following. So remember, I said that Zorn's lemma was one of those results. You can think of it as a theorem, right? It's a consequence of the axiom of choice, but it's actually equivalent to the axiom of choice. So if you wanted, right, or let's say it this way, from the axiom of choice you can prove Zorn's lemma. From Zorn's lemma you can prove the axiom of choice. And it goes like this, so let's let P be a partially ordered set or maybe I think maybe I like to say it better with if P is a partially ordered set where every chain has an upper bound, then P has a maximal element. So it's possible that in every class you've taken, you've never seen a statement of Zorn's lemma. Now you've seen it. And it's maybe a bit mysterious. I mean, somehow I feel like the axiom of choice, once you understand what the statement is really telling you, right, that every time you can, there exists a choice function, so you can pick an element from each of the sets. This is a little bit less transparent. What's the opposite? Less transparent, more opaque, right? It's certainly not clear that this follows from the axiom of choice. But it turns out that it's equivalent to the axiom of choice. And we're actually going to use the axiom of choice, we're actually use Zorn's lemma to prove a couple of things in this class, right? So let's leave it off here and we will pick up with an example, right, of using Zorn's lemma to prove some other somewhat familiar mathematical fact. All right, so we'll see you next time.